Okay, so this is lecture 2 to PHY119, and we're talking about quantum communication. So, last time we talked about the non-cloning theorem, and we saw that it's actually not possible to make a copy of an unknown state. So, and now I want to talk about what happens if you make a measurement on a quantum state. So when quantum mechanics was formulated, there are these axioms, some of which you know. So postulate number 1 says that at each instant in time, the state of a physical system is represented by a ket, psi, in the space of states. So these are column vectors. This you already know. The second postulate says that each observable attribute of a physical system is described by an operator that acts on the kets that describe on the system. So by convention, an operator hat m, so the hat denotes that it's an operator that it does something onto the state. Acting on a state psi is denoted by left multiplication. So this is given by equation 3 over here. So psi changes to psi dash after hat m has acted upon it. So yeah, so psi is a vector, so m is supposed to be a matrix. So I think this you already know. You may have seen it in a slightly different form. But so m would usually be a unitary that we'll discuss a bit more, and we have been discussing. And the third postulate of quantum mechanics states that the only possible result of a measurement of an observable at m is one of the eigenvalues of the corresponding operator. So what does this mean? It means that if you measure a certain operator, you will only, so the state would end up being in one of its eigenstates, and what you measure, the value of the measurement corresponds to its eigenvalues. So let's have a look at this in a bit more detail. So this would correspond to the statement that one cannot take a measurement without perturbing the system. It means if you try to measure the system, you change it. So formally, these are the rules that you have to obey if you're trying to make a measurement. So it says that a measurement is described by a set of measurement operators mi, and we require that summing over mi dagger mi is equal to the identity. So this identity would have the dimension of the system. So if you have a qubit, you would have a two-dimensional identity matrix. If you have 2 qubits, you would have an identity operator of dimension 4, and so on and so forth. So each possible measurement outcome, we denote this by, we label it using I, and this will occur with probability P of I given by, so mi dagger, mi overlapped with psi. And we require that the probability sum to 1. So, and this is just a Born rule. So what this means that, so giving an example, we could be projecting onto, say, just a computational basis. So one of these m's would correspond to projecting onto the state 0 or projecting onto the state 1, and you require those to sum up to 1. And had you obtained outcome I, then the state of the system after the measurement is given by this identity over here. So you have to measure an operator acting on the quantum state, and the denominator is just a normalization factor. So this means that if you act on the quantum state with this thing, you might change the amplitude. So you might change the amplitude of the state, and the bottom here simply just turns the vector back into something of norm 1. So, oh, hello there. Okay, so now let's have a look at some simple examples. Oh, actually, no, before that, I want to talk a little bit more about the dimension of the operators and the vectors, so on and so forth. So you may have seen that the Z operator in matrix form looks something like this. So it has a 1 and a -1 on the diagonal, and the off diagonals are 0, and the X has diagonals 0s and the off diagonals 1s. So let's do it on the board as to how you would, how you would manipulate the qubit, well, psi over here using these operators. I want to stop presenting. Okay, to present a window. Wait. This thing. So. Sorry, I hope that you're seeing a whiteboard. Is that correct?
Yeah, we can see the whiteboard.
Okay, awesome. So, oops. So if I have an operator Z, which is 1 minus 1, it acts on, let's say that it acts on, is the hat? Let's say that it acts on the state psi, which is alpha beta. So this is very simply alpha minus beta, right? So matrix, this is just matrix multiplication. So you put a -1 on the beta. Similarly for the X, so if you have an X psi, so you have 0, 1, 1, 0 acting on alpha, beta. This would give you beta, alpha. Because what this does is that it will flip these two components. So what's on the top goes onto the bottom, and what's on the bottom goes on the top. So it may be slightly less obvious that the Z operator, okay, let's just clear this. It'd be slightly less obvious that the Z operator 0, -1 can be written in bracket notation like this. 1 -1. So how this comes about is that it comes from how you do tensors in QM. So basically, it's actually very simple once you get your head around it. So if you have two things, so if you have two qubits, psi and phi, so to describe this particular system, you would say, okay, this is a tensor, and what this looks like in bracket notation is that you go, let's say this psi is alpha 0 plus, alpha 0 plus beta 1, and let's say phi is equal to delta 0 plus beta 1, then this becomes just alpha delta 0, 0 plus alpha, sorry, this is meant to be a delta. Delta, okay, let's choose another character, gamma. So if alpha delta 0, alpha gamma 0, 1, beta delta 1, 0, and beta gamma 1, 1. So you literally multiply out each of the components, and that's how you tensor two qubits together. Now, as we're discussing, the operators are meant to be matrices, right? And so let's just clear that again. So if you want something that is an operator, you need something that is 2 by 2 for something that's acting on a qubit. So what you would do is that, okay, so if I have psi tensor psi again, so oops. So you have psi ket tensor with psi bra. So this thing is alpha beta, and this thing is alpha conjugate, beta conjugate. So this thing would give you, so obviously this has basis 0, 1, keeps happening. And this, as I mentioned, 0, bra, 1. So the components, if I write this out properly, would have alpha squared, 0, 0, and alpha beta conjugate, 0, 1, and beta alpha conjugate, 1, 0, and beta squared, 1, 1. Right. So this thing is an operator, and the components are of the, like, so the coefficient in front of the respective components can be worked out like that. It might take you a bit to wrap your hand around it, but once you get used to it, this is pretty simple. Okay. So let's go back to the presentation. Cool. Okay. So if I look at the Z operator, it looks like a ket 0 bra 0 minus a ket 1 bra 1. And an operator X looks like a ket 0 bra 1 plus a ket 1 bra 0. And yes, so equation number 8 is what I just did on the board. So for example, once again, using our beloved state psi alpha 0 plus beta 1, we can, say, for example, perform a projective measurement. So that will look like those two elements on equation number 9 there. So this means we're measuring whether the state is occupying 0 or whether it's occupying 1. So yeah, so you can check that M0 dagger, M0 plus M1 dagger, M sums to the identity. So the identity acting like qubit just means that it leaves the object unchanged. So we can do this in either matrix notation or bracket notation. It doesn't matter and should give you the same result, obviously. So if I do this on the board again, so I want to do equation 10 on the board. If I want to do M0 dagger, M0, so here I have, M0 is equal to 0, 0. So if I apply the dagger to it, this remains unchanged. What would change, though, is that if this is something that looks like the X, so if I have 1, 0 here, so instead if I want to put a dagger on this, this would become a 0. Yeah. This would become a 0, 1. So I'm not sure if you've seen this before. If you haven't, don't worry too much about it. Okay, so I have M0 dagger, which is exactly equal to M0. So now if I put those two things together, M0 dagger, M is just 0, 0. Then now you have the M0, 0. Okay, so this is an overlap of 0 and 0. So this thing is equal to the scalar number 1. So this at the end just gives you 0, 0 back. Okay, so now if I want to do, okay, I think I need more space in that. So now if I want to go, okay, what's the overlap with 0, 0? This, if I write it out, this would be alpha dagger 0 plus beta, well, conjugate, sorry, 1, giving you 0, 0, and then you have alpha 0 plus beta 1. Okay, so every time you see a 1 overlaps with 0, you end up with 0. And so this will just get killed. So this interacts with the 0, will give you 1. So you have, so what's not killed is, you have, okay. So you end up with alpha 0, 0, 0, alpha 0, right? So this thing becomes a 1. Alpha here is just a scalar, so we can pull this up front. So you end up with alpha, alpha absolute value squared plus 0, 0, and this becomes a 1 scalar. So you just end up with alpha squared. So this is as expected, because if you start off, wait, let me go back to the presentation. Now window. So this is as you would expect, because if I have a state that's in alpha 0 plus beta 1, then of course measuring the portion of it that's in 0 will just give you alpha squared. So this just formalizes it a little bit more. So yeah, so equation 11 there, it was just what I did on the board. Cool. Now we're ready for our first quantum cryptography protocol. So the two elements that we need are, we know that we can't copy quantum states, and we can't measure them without disturbing the system. So this implies that if I give you one copy of a particular quantum state that is unknown to you, you cannot characterize it. Well, so the emphasis there is that you only have one copy. Why is that important? Because if I give you many, many copies, and eventually, and you can perform a repeated experiment on that, eventually you will figure out what it is. So why would that be? So if I tell you that a quantum state is either a 0 or plus, so if you keep measuring the 0 basis, you will always end up with probability 1. So in that case, you know that it's for certain a 0. And if you measure in the plus basis and you always get probability 1, then you know that it's a plus. So let's make those statements slightly more rigorous. So we have our quantum key distribution protocol B84. So this is named after Bennett and Brassard, who invented this protocol in 1984, I believe. So the task here is to establish a secret key between two communicating parties who are conventionally named Alice and Bob. So they will make use of two bases, so the eigenstates of Z and the eigenstates of X. So Z looks like this and X looks like that. You've seen that many times. So we know that the normalized eigenstates of Z are 1, 0 to 0, 1. So for X, this is the 1 plus 1 and 1 minus 1. So I will do, once again, the protocol on the board. So the protocol goes as follows. So you have Alice, who is trying to send something to Bob. So remember, all we're trying to do is to establish a secret key that is random. It doesn't really matter, at which bit, what the value of the actual bit is. So you'll see what this means in a second. So Alice chooses a classical. So remember, they're trying to establish a classical string, which are unknown to an eavesdropper. So Alice chooses. So remember that if we're trying to send classical information, we are embedding this in a quantum state. So let's say, remember that if I have Z, then if I choose this classical bit to be 0 or 1, then I'm sending 0 or the 1. Oops. So these are just my encodings for now. So if I have the basis X, if I want to send 0, I encode this in the plus. And if I have the 1, then I encode this in the minus. Okay, so the protocol goes like this. So Alice chooses her classical bit. So for example, this can be a 0, a 1, a 1, a 0, and a 0, and a 1. And then now she chooses the bases. So, and these are all chosen at random. So she may choose to send in the Z, in the Z, in the X, in the Z, in the X, or in the X. So now that she's chosen her bit and her basis, she will use a corresponding quantum state. Let me just drop this in the box. So she sees a 0 and a Z, so she'll send the quantum state 0. Ket 0. There's a 1 and there's a Z, so she'll choose the quantum state Ket 1. Now she sees a 1 and there is an X, so she'll choose a state minus. Now there's a 0 and a Z, so this is just a 0, and this is a plus, and this is a minus. So remember, of course, the 0 and the 1 are orthogonal to each other, and the plus and the minus are orthogonal to each other, but the 0 is non-orthogonal to the plus or the minus, and the 1 is not orthogonal to the 0. Sorry, the 1 is not orthogonal to the plus or the minus. So now she will send this to Bob, and Bob will choose to randomly measure in, once again, the X or the Z. So Bob doesn't know what measurement basis Alice has chosen to prepare it in at this stage. So Bob might choose to measure in, let's do a different color. So Bob might choose to measure in, say, the Z, the X, the X, the Z, let's go with the Z, or the X. Okay. So now that they've done this many times, after Bob has received everything from Alice, Alice will tell Bob publicly what basis she has chosen to prepare the qubits in, and they compare which ones they've and they match the ones where the preparation and the measurement are done in the same basis. So this is saying that, okay, so Bob says, so Alice says, okay, for the first qubit, I've done it in the Z, and Bob goes, okay, I've measured in Z, so they keep this one. So for the second one, Alice says, I've done it in Z, and Bob says, okay, I've done it in X, so we discard this one. So this one, so for the third one, they say, okay, we match in X, so we keep. And the fourth one, they keep because that's done, oops, because that was correct. And then this is incorrect. And the last one is correct. Well, okay, they match versus not match, not as in correct, as in, yeah, anyways. So for the ones that they do match, Bob would have obtained a 0. And for this one, Bob would have obtained a 1 because, you know, if Bob measured an X and Alice prepared a minus, then Bob would have measured minus with probability 1. And so Bob writes down 1. So here, Bob knows that he has a 1 here. Wait, sorry. No, this is a 0. 0. And here, Bob has a 1. So this will be the secret string that the two parties end up sharing at the end of the protocol. So why did they choose to chuck away these ones? It's because if Alice has sent a state 1 and Bob has measured an X, it means that Bob has no idea what Alice has prepared in. And same goes for this. So if Alice has prepared a plus state and Bob has measured in the Z basis, so to make it even more explicit, so if Alice has sent this state at 0 plus 1, oops. So by measuring in Z, Bob has effectively projected onto this basis that we did before. So with probability a half, you get a 0, and with probability a half, you get a 1. And this is not ideal, certainly, because it means that no matter what Alice has sent, the outcome on Bob's side is completely random. So is that clear, or does that? Okay. Cool. So this is our BB84 protocol. So when we say something is secure from a cryptographic sense, it means that, so of course, in real life, this would be a very, very long string. So it may have n bits in total. So it means that the probability of an eavesdropper to correctly guess the value, or like the identity of this bit, this bit string would be proportional to something like, okay, would be proportional to 2 to the power of minus n. So this just means that essentially she's just guessing what the bit values are. So the longer the bit string, the less likely she is to get it correct. And this is, of course, good news because for cryptography, you want something to scale as a negative exponential rather than something that's polynomial. Okay. I have on the lecture notes to talk about what error rate an eavesdropper would introduce if she were to use a send and intercept strategy. So maybe I'll just do that as an example. So what's a send and intercept reason? I think I need more space. So what's a send and intercept strategy? So for example, what this means is that if I have, okay, let's use blue again, maybe black. So for example, if Alice sends this string, let's go 0 and 0. So for example, this is the string of quantum states that Alice has sent to Bob. So if Eve, an eavesdropper, was to simply steal all of these and she measures it herself and then sends her measurement results back to Bob. So how would this be? She would say, okay, Eve would go, okay, I don't know what Alice has measured it, prepared in, so I'm going to measure in a basis of my choice. So I go Z, Z, X, X, Z, X, Z. And then, so here, now she will obtain an outcome, right, for each of those states that she measured. Then so whatever she measured, she prepares the state again and sends it to Bob. What would be the error rate that they introduce when Alice and Bob are checking for their final key correctness count? That makes sense. So, okay, does either of you want to have a go at guessing or calculating what this might be? If not immediately, I will tell you the answer next week.
Is it less than a half? Because I feel like Bob gets a half, so and hopefully this is more like better encryption, so hopefully it's less than the receiver.
Okay, so sorry. So there is a step in there where Alice and Bob checks whether they've prepared in the correct basis, right? And then so everything that they do not correspond, they will discard. So in principle, the key that Alice and Bob share at the end should be completely identical. It'll be a factor of half shorter than what Alice has sent, which is fine because you're just discarding something. So Bob would end up with half the key that Alice has sent, but whatever half they share are identical. So those are perfect. So this is a scenario where somebody else who's not authorized has stolen the entire train of qubits that Alice has sent, and they've measured exactly the same as Bob. But of course, this person cannot check with Alice which basis they've sent in. And then this person sends back whatever they got to Bob.
Okay, yeah, I get it.
So of course, okay, let's have a look at what happens in the next step of the protocol. Wait, and then that might give you a better clue. Okay, so this is now Eve, right? Oops. So Eve has measured in Z. So if Alice prepared a plus, then the measurement outcome of Eve might just be a 0 because that's the basis that she measured in. So remember, if she measures at Z, then she'll either get a 0 or 1 randomly. So Alice has prepared in 0, but Eve has measured in the wrong basis here. So she'll either end up with a plus or a minus. Let's just go plus. And this is minus. So now here, Eve has actually measured in the same basis as Alice. Oops. So definitely, she will obtain a minus. Sorry, this keeps happening. So she'll get a minus. Here, of course, Eve has measured in the correct basis again, so she'll get a 1 for sure. And now this is random because Alice is sent at 0 and she's measured in X, so she might get a plus. And so a 0 and a Z, Eve would end up with a 0. Is this obvious what I'm trying to get at?
Yeah, I get so she ends up with a longer string, and they're not actually using most of the a lot of the stuff that she's got in the string, right? Is that because she doesn't have the public?
So
or is it?
It is okay to end up with a shorter string. That is not the problem. So whatever. But so what you don't want them. So what you do not want to happen is that Bob. So you don't want Eve and Bob to share the same key with Alice. So for example, if the key that Alice shares with Bob is 0, 0, 1, 0, 0, 1, 1, 1, you care if Eve actually knows for sure what some of these bits are. So you don't care that Alice and Bob ends up with a shorter key that Alice has generated, but you do care that that the eavesdropper knows what it is. So I can leave you to think about this for a bit longer and tell you the answer next week, or you may have a few more minutes to think about it at your back of mind. Okay, let me tell you the answer next week. This was originally going to be an homework exercise or a mock exam, and of course the exam's not happening anymore. Okay. A window. Okay, so so I think everything I talk about is actually in the lecture notes that I uploaded online. I actually found a few errors since then, so I uploaded the correct version. So okay, so let's talk about some of the experimental implementations of the protocol. So since it was, so this is actually a very simple and elegant protocol that, you know, a second year or third year student could have come up with. But it took quite a while to come up with a security proof to say that it's actually unconditionally secure. And currently, it's actually a very active area of research. But the physics is all known. So the two Bs invented the protocol in 1984, and the first experiment was conducted in 1992 using something that looks like this. So I think they were using diodes and photon counters and possibly, Paco cells. So they use something that has the electro-optic effect to convert the photons, which were originally produced in a horizontal orientation, into left and right circular. So we talk about zeros and ones, right? So in reality, this will correspond to the polarization of a photon in that particular experiment there. So they were using H and V for the Z basis, and then for the X basis, I think they were using H plus IV and H minus IV. So those two are the two different bases that we're using. So very ancient. And now, after a couple of decades, we can actually put some of these on a chip. So once again, I think this experiment was done, I believe, in Bristol. So a chip would look something like this. So remember, all you need for the distribution protocol is two complementary basis sets. So here, I think they were using time bin, which means you produce a photon that is in a superposition of either being in the first time bin, the second time bin, or a superposition of those two. And you can do that, and you can tune the phases. So the modern protocol actually changed quite dramatically after they figured out that you don't necessarily need a single photon. You can just use a very weak laser pulse. So you probably haven't encountered quadratures before, like we talk about X and P in a harmonic oscillator. But using that particular encoding, using similar principles, so the principles are just, so the non-cloning theorem in combination with non-orthogonal states. So if you combine those two, you can actually do things with just a laser. And the Chinese group managed to get this on a satellite. So you might have seen this since they were launched in 2016 or 2017. It attracted a lot of attention. I think even more so in the non-quantum community, because it's impressive, but it's also partial hype. I think the most impressive thing that they managed to do is to actually align the laser beam from the satellite onto the ground station. Because remember, if you send a laser beam onto the moon, it'll diffract. So, something that you start off with on Earth that's 2 millimeters will become 5 kilometers on the surface of the moon. So, similar principle. If you shoot something up from the ground station here onto a satellite that's moving at very high speed, because this is a low Earth orbit, then yeah, the spot gets very big and the losses become a problem. But nevertheless, they managed to do this experiment. So now everybody, including the UK, the US, Austria, everybody's trying to do satellite QKD, because, if China has it, then we also have to have it. Yeah, so I think originally the US wanted to do something like this a long time ago, maybe like even 2 decades ago. And then there is some bureaucracy, and then they say, oh yeah, we'll never get the pointing and tracking right. So if you start off with a small beam, if you start off with a wide beam on the surface of Earth, then this thing so the beam getting to the satellite might be narrower, and vice versa. Then if it's too narrow, it means it's very hard to track. But if you make it bigger, then you're very lossy. But now that it's shown to be able to, somebody's able to do it, therefore it must be doable. So I think the UK has actually injected like some $24 million into the quantum communications hub, which is paying for my salary at the moment. Yeah, everybody's trying to do it. So, okay, so before I said that this protocol is unconditionally secure. So of course, when you say that, everything comes with the caveat. It is unconditionally secure given that you build the exact device that you have on paper, which is never the case. Because, okay, so the protocol that we discussed, we assume single photons, and we assume that everything's perfect. But in reality, we don't really have single photon sources, and people are trying to use, or have been thinking about using laser pulses. And of course, you might end up with more than one photon in your pulse. So if you have more than one photon, then somebody can split it and measure it, and the protocol is not secure anymore. And you have losses and attenuation. So this would be a problem if you're trying to go to long distances. So remember, the modern communication system, what happens is that you send a series of pulses through an optical fiber, and every, I think, couple of kilometers, or every set distance, something would measure it and then amplify your signal. And that is actually the exact problem with quantum communication. You can't amplify because, well, okay, so because you can't measure, you can't amplify. Because if you've measured it, then by definition, you've stolen the state. So another problem would be that you need true random number generators. So remember, when Alice is trying to generate her key, she would need to choose randomly her bit string, her classical bit string, as well as which bases to prepare her state in. So, and we assume that information is completely hidden from a potential eavesdropper. And of course, we know that there is no deterministic protocol using classical computers that can generate true random numbers. So the solution there would be to use a quantum number generator, which you might have heard about. And there are some side channels, so an eavesdropper might be able to shoot some light into Alice's preparation apparatus and find out which bases she's measuring, and so on and so forth. So yes, this is a currently very active area of research. So That's the last one of my slides. Does anyone have questions from today? If not, next week I'll review the answer to the eavesdropper attack protocol, and we'll talk about something very exciting, entanglement and super dense coding. And you might have heard a lot about it. So next week we'll formalize those ideas. So if nobody has questions, I'll see you next Monday, I think. Monday.
Thank you.
Cheers.